our three-phase inverter. Previously, we discussed the principle of pulse width modulation, and we discussed the different power electronic circuits used in electrical drive systems or variable frequency drives. Today, inshallah, we are going to focus our discussion on the three-phase full bridge inverter, which is mostly used for three-phase AC drive or three-phase variable frequency drive. طبعا شباب يعني we said three phase. Do we have other number of phases? 4, 5, 6. Do we have such machines in our life? Who can answer me, شباب?
Yes.
Do we have such machines?
You mean more than three phase?
More than three phase. Do we have?
I don't think so.
No, we don't.
We didn't discuss something like that before. طيب يعني it's not in our course, but already we have شباب. We have other types of machines. If you Google it, you will find that we have 5-phase machines, we have 6-phase machines. Okay, it's called also يعني multi-phase, and it's used mainly to increase the reliability of electrical machines. So if you have more phases, this means if you have one of the phases fail to work due to any problem in protection, open circuit for instance, so other phases can work in different way. This is very important, شباب, in terms of continuity of loading or reliability. And it's used in critical loads, like for instance in ships, okay, big ships in marine application. We need very robust controls and reliable machines. So we use multi-phase machines. Multi-phase, like what? Like 5-phase, 6-phase, and so on. So if you have, for instance, in 6-phase machine, and one of the phases has a problem due to anything, and one of the phases became faulty, so we can disconnect this phase and operate the machine as 5-phase only. This can be happen up till operating the machine at 3 phases. Okay, so for that, شباب, we prefer to use more than 3 phases in critical loads. Okay, so we have شباب. But for now, يعني the mostly used one in industry is 3-phase one. For that, we are going to take care about the 3-phase. So if we have more phases, شباب, what do you think? And here we have now 1 DC link and 3 arms. Each arm will take care about supplying one of the phases of the 3-phase system. If we have more 5 or 6 phases, what do you expect the shape of the circuit will be?
It will be 5 arms.
Exactly. So the number of phases, شباب, can be represented by some extra arms. So if we have, for instance, 5 phases, we can make 5 arms. If we have 6 phases, we can make 6 arms, which can be considered as twice of this circuit shown here. So this is the idea of full bridge converter now. Right, how it can operate, شباب? Now we have here 6 switches, 1, 3, 5, and the naming is standard, شباب. 1, 3, 5. Odd, okay, and in the lower 3 switches, 4, 6, 2. Why we started from 4, not from 2? Because all of time we need a difference between upper and lower switch, difference of 3. So here Q1 at 3 it will be Q4. Here Q3 at 3 it will be Q6. Here Q2 you can now subtract 3 it will be Q2 because we have only 6. So the difference between upper and lower numbers all of time will be 3. So the upper switches 1, 3, 5, the lower switches 4, 6, 2. This is standard for the names of 3-phase inverters. How it works, شباب? Simply, we need to apply some pulses for the 6 switches in order to obtain the required output voltage. Last class, we discussed that we can operate the inverter by using square wave in order to get square wave output. And also we discussed that we have another technique called sinusoidal pulse width modulation. In sinusoidal pulse width modulation, we will have higher resolution output with lower harmonics. And we prefer to use PWM for that. So in order to understand the operation of this circuit, let's firstly start with square wave, and after that we will switch to pulse width modulation. For square wave operation, Shabab, we have two well-known techniques for three-phase inverter. By the way, the circuit we discuss here, Shabab, called three-phase two-level. Why two-level? Because we said before, Shabab, two-level because we have 2 points for DC link. We may have, Shabab, different circuits with many levels. How? Just by splitting this DC on capacitors. So we will have some other points, some midpoints between capacitors, and can be used in order to achieve many levels of voltage, which is called the multi-level inverter. Multi-level inverter. But now this circuit is considered as two-level inverter. Okay. So for the two-level inverter, as you can see here, we are going to make a sequence of pulses for the 6 switches like that. We will start from 0 to pi, which means first 180 degrees. Then from pi to pi by this way. So we will conduct the switch for 180 degrees and disconnect the switch for another 180 degrees. And you can make the sequence like that. Start by G1, which will be the gating pulse of switch 1, then 2, 3, 4 in that way. And keep a phase shift between each switch by 60 degrees. So here at pi over 3, we will start the second switch. Then at 2 pi over 3, we will start the third switch. طبعا we said يا شباب upper switches are 1, 3, 5. 1 will be responsible for phase A. 3 will be responsible for phase B. And 5 will be responsible for phase C. So in order to have 120 degrees phase shift between the 3 phases, you have to start phase B switch after phase A by 120 degrees. For that, you will find G3 has started after G1 by 120 degrees. And similarly, G5 will start after G3 by another 120 degrees. So this is now 4 pi over 3, which is 240 degrees. Is it clear يا شباب؟ طبعا add this. طبعا this is for upper switches G1, G3, G5, and all of time يا شباب, the lower switches have to be complemented to the upper switches. Otherwise, here in the circuit, if 2 switches on the same arm are turned on, this is going to make a short circuit on the capacitor. Is it right, شباب? ها شباب, is it clear? يعني if Q1 and Q4 are turned on at the same time, this is going to make a short circuit here. We are not going to supply the load now. So it's prevented to make Q1 and Q4 on or turn it on at the same time. For that, all of time, G1 has to be G4 complement. Okay, شباب. And this is also for Q3 and 6 and Q5 and 2. This is to avoid short-circuiting the capacitor. So this is the way now, شباب. As you can see here, we have G1 turned on from 0 to pi, and G4 has to be complemented. So it will be turned on from pi to the end of the period at 2 pi. So this is the way of square wave of 180 conduction. We have another way called 120 conduction, but for now, we need only one case to understand how we can switching on and off the three-phase inverter, and after that we'll discuss the PWM. So now, Shabab, based on the sequence of pulses here, let's see together the shape due to the switching. For instance, here in the beginning figure, this slide, Shabab, it's just new. I added before of the class, so you will not find it now in your notes. So please understand it here with me, and I will add it to you after the class. As you can see here, Shabab, we have inverter connected to three-phase loads. Here, switch 1 is on, switch 6 is on, and switch 5 is on. So this means A is active high, C is active high, and B is active low. So this means now, Shabab, phase A and C will be connected to positive, and phase B will be connected to negative. Is it clear, Shabab? Is it clear? We have here 3 impedances. Due to connecting 1, 5 in positive, so we have phase A and phase C in positive and in parallel with each other like that. And for phase B, because the lower switch is turned on, so in this case, the phase B will be connected to negative VDC. So it will be alone in negative like that. So for now, Shabab, we have 2 impedances in parallel. You know that the impedance, if we have 2 equal impedance, the equivalent of the 2 parallel impedance will be 1/2 of the A of one value of them. So if we have Z parallel with Z, so the resultant of the parallel impedances will be Z over 2. So finally, you will have like that. Z over 2 and Z. And here you have VDC or VS, for instance. So what will be now the value of VA and VB? Take care that this is a neutral point, and this is here considered now as B, and this is here for A and C. So VAN and VCN are equal because phase A and phase C are in parallel. So what will be the value now, Shabab, for VA and VC? Like that. This is now considered as VAN or VCN as well. And here, this is VBN. Is it right? What will be the value, Shabab, of VA in terms of VS? What we can do?
Voltage divider rule.
Voltage divider rule, exactly. If we apply voltage divider rule, Shabab, you will find that this impedance is 1/2 of that impedance. So this means now that the voltage here will be, Shabab, let's calculate it if it is not clear. And we can say I here, I equals VS over 3 over 2Z. So we can say now it's 2 VS over 3Z. Is it right?
Yes.
So what about the voltage drop on the first phase here, or VA? We can say now VAN equal Z over 2 multiplied by I, which is Z over 2 multiplied by 2 VS over 3Z. So Z will be omitted here, so it will be now VS over 3. Now, if this is VS over 3, so the remainder will be 2 VS over 3. Is it right? But take care that the polarity of VBN is opposite to the voltage drop here. So this means now VAN equals VCN equals VS over 3, and VBN equals minus 2Vs over 3. So this now, Shabab, these analyses are for the first connection. Take care that if we have two parallel phases, the resultant value will be 1/3 of the DC. And if you have single connected phase, the volt will be 2/3 of the VDC, as you could see here, Shabab. Also take care that if the upper switches are on, the volt will be positive. However, if the lower switch is on, like here, the volt will be negative. So finally, and we have here many modes, you can follow the circuit, and finally you can get the output three-phase voltage like that, Shabab. You will find sometimes volt equals 1/3, like the first part here, then 2/3, then 1/3 again. This is in positive, and similarly in negative. This is for VAN, Shabab. For VBN, it will be shifted by 120 degrees. So we started here at 0. This is now 2 pi over 3, 120 degrees. And after that, at 4 pi over 3, 240 degrees. So this will be the shape of the three-phase voltages if we use the square wave conduction called 180 degrees. طيب شباب, in order to analyze the performance if we make square wave operation, let's see together. This is here just some analysis using MATLAB. I applied the 180 degrees, okay, for a certain DC value of supply. This is 0, so this value is 2Vs over 3, and this is here Vs over 3, and this is a 0, our reference volt. So this is now minus Vs over 3, and this is minus 2Vs over 3, and so on, Shabab. I applied this to inductive load current. Inductive load, it means RL load. The current waveform, Shabab, was like that. يعني طبعا there is an equation for current. We discussed it last class for single phase. The current, Shabab, will be يعني all of time will be V over the impedance. Okay, but you have يعني a differential equation which has switching or transient solution and steady state solution. So you will find a part of exponential in the current. For that, the waveform will include exponential part all of time. So this is now, Shabab, the waveform of the current. Is it sinusoidal, Shabab? Is the current here considered sinusoidal waveform? Or we have a lot of harmonics now?
Yes, harmonics.
We have a lot of harmonics. In order to evaluate any waveform, we have some harmonic evaluators. We said that THD value is one of the well-known used harmonic evaluators. As you can see, by analyzing the voltage here, Shabab, you can find that the THD value is 31%. And you can see that the harmonic factors are very high for small frequencies. So here we have harmonic order, Shabab. Harmonic order means if we said fundamental, so harmonic order is number 1. So this is now representing fundamental, and it's going to be up to 100%. We said before, we refer all of time the spectrum to the fundamental. So fundamental is going to be 100. So we cut it all of time in order to zoom in to see the harmonic contents in the low values. So as you can see here, we have like this may be third, this is fifth. So fifth here has a component. This is fifth order. Seventh has a component. 11th has a component. 13 has a component. But you can see third is 0. Fifth is also sixth or ninth. Sorry, ninth is 0. Okay. Then 15th is 0, and so on. Actually, we have Fourier series for the 100 conduction. unfortunately I didn't write the relation here, but there is a well-known Fourier, not Fourier, there is relation for the analysis of the voltage here, and if you substitute in the waveform voltage, you will find that third harmonic and multiples are 0. And we will discuss in detail شباب third harmonic in three-phase systems after discussing the inverter here. So this is one of the advantages of square wave شباب, square wave operation using 180 conduction. The third harmonic and multiples all of time will be 0. We have also another note شباب, we don't have any even harmonics. All of harmonics are only odd because شباب, in the operation of three-phase inverter, positive and negative cycles will be identical. So you don't have any even harmonics. So we will have only odd harmonics شباب. طبعا first is the fundamental, third here equals 0, third and multiples are 0. You will find 5th, 7th, 11th, 13th, 17th, and so on. But as you can see, the value is high. It's here around 20, around 15, around 13, like that. So these values are very effective. Because of that, شباب, the THD value is 31 here. If we analyze the current, we could see in the previous slide, you will find طبعا fundamental is also 100%. You will find that there is a component for fifth. But طبعا يا شباب there is attenuation for the current harmonics. What is the meaning of that? Now the first component is 100. When we calculate the current component, it will be 100 also. What is the relationship between I and V? I equals V over Z. Is it right? صح يا شباب?
Yes.
طيب. We know that Z equals R plus, here this is inductive load, so it's now omega L. R plus J multiplied by omega L, which is 2 by F multiplied by L. So JL 2 by F. This means شباب, that the impedance is frequency dependent. So at fundamental, when you calculate the fundamental current, you just need to divide V over Z, where the imaginary part will depend on F. But when you consider the fifth harmonic order, in this case, the imaginary part here will be multiplied by 5, because the frequency will be 5 times fundamental. So this means the impedance at fifth harmonic order will be higher. If it is only inductive, it will be 5 times. Okay, but here it's both, so we cannot exactly know the value, but it's higher than the fundamental impedance. For that, you will find here fundamental current is lower than fundamental voltage magnitude. Question. This is at fifth order. Can you see here at seventh order? The impedance at seventh order شباب is higher or lower?
Higher.
Higher. So the higher the switching frequency, the higher the impedance, and the lower the harmonic contents in current. This expression is very important. Again, the higher the switching frequency, the higher or the lower the harmonic contents in current. Why يا شباب? Because Z will attenuate the harmonic contents. طيب. From here يا شباب, we got a THD value for current, which is 7.5. By the way, this value is not standard, as we discussed in the previous class. The current, if we are going to connect this energy to grid, for instance, using single-phase inverter or three-phase inverter using any renewable energy source, so the current has to be less than 5%. This is for low voltage standard. So 7.5 is not impossible to be connected to grid. In order to connect this energy to grid or this power to grid, you have to reduce THD value of current below 5%. How we can do that, Shabab? What do you think? If we have the same load like that, and you know the grid, by the way, the grid is inductive, so it will be very similar to that load. How we can reduce the harmonic contents in current? Hey, Shabab, is there any suggestion?
Using a filter?
Filter is one solution. Filter already, we have many types of filters, Shabab. And the idea of filter design is based on resonance. You know resonance? In resonance circuit, we design resonance circuit based on a certain frequency. And at this certain frequency, the impedance will be minimum. So if we add, and if we have source and load, and you need to add filter here, filter F, this impedance will act as short circuit at the required frequency. So for instance, you can make filter for the fifth order by making the impedance at fifth order equal 0 or very small. So in this case, the fifth order will flow here in this filter and other orders will go to the loads. So this means, Shabab, if we have many orders, we need to make many filters for each one. This is called, Shabab, a passive filter. Passive filter, which is working only for one harmonic order. We may have something called the band pass filter. Band pass filter can contain or absorb some harmonic orders. And we recently have something called active filters. Active filters are designed to absorb all of the harmonic contents. It's not like passive elements, L and C, but it's based on inverters. It's called active filter. Type. In terms of control, let me give you an idea. Now, when the fifth order here is high, is 20, we got fifth order here high. But what about if we could shift this value of the fifth order, which is 20 now, if we could shift this value to higher frequency? If we could shift the fifth order here to order number 50, for instance. And between these two harmonic orders, or between fundamental and this value, there will not be any harmonic orders here. What will happen to the current, Shabab? Is it going to be similar 7.5?
It will decrease.
It will decrease. Why? Because the first highest component, which is 20, will appear at order number 50 instead of 5. And at order 50, as you can see here, you have here already some few components, maybe 2 or 3 like that, but it's not appearing here because the impedance is very high. So we expect that if we could shift this value 20 to a frequency order of 50, this will be much more attenuated here. And in this case, you will remove all of these harmonics. Actually, this is the idea of pulse width modulation. So we have many techniques, Shabab, for PWM. We have sinusoidal. We have something called third harmonic injection, space vector selective harmonic elimination. We will discuss some of them, inshallah. So, principle of sinusoidal wave, Shabab, we discussed it previously. We just to compare modulating waveform with sinusoidal or with carrier. Carriers are used just to sample the waveforms of sine wave. So, here, Shabab, for instance, this is our modulating waveform, which means this waveform will give you frequency like that frequency exactly. And this inverter, when the output of this converter or inverter will give you frequency like that value. And the magnitude will depend on the peak value of the supply. We discussed this شباب in last class. Is it right? We discussed modulation index and frequency ratio. Is it right?
Yes.
Did we type? Okay, good. So by controlling modulation index and frequency ratio, increasing frequency ratio, are going to get much more samples and the pulses will be higher. And in this case, you will have higher resolution. So this is a pulse simulation as we discussed in single phase. It has the same idea, شباب. So here we have, for instance, an example for this is over modulation. Neglect this slide يا شباب. We may return it back later to this slide. This is for over modulation, but for now let's focus on under modulation performance. For instance, I made here under modulation performance at MD, or modulation index, of 0.95, but I applied different switching frequency. So I started with a frequency ratio of 21. 21 frequency ratio, which means the first highest harmonic orders will appear around 21. As you can see here, the value maybe this is at 19. So at 19, it's almost close to 30. Okay? If we apply frequency ratio of 51, this means now we shifted the harmonic orders to around 51. So as you can see here, at order number 49, we have the same value we could see here. So it's shifted now, يا شباب. Shifted. Why it's shifted? Because just to increase the frequency. If we move the frequency more at frequency ratio 101, so around 101, it's appearing now at order number 99. So the value will be as it is, but it will be shifted only due to increasing frequency. For that, you will find that THD for volt is almost constant. صح يا شباب؟ THD value in volt will be the same or almost constant. Why? Because we just shift the harmonic orders. We did not filtering these orders. It still exists, but it's just shifted to higher frequency. Actually, this is very effective for current. How? Let's see the performance in current, شباب. Firstly, this was the performance at frequency ratio 21. So for that waveform, you will have current with higher value also here. And it seems here, شباب, at that value, the impedance is not that high. The effect of frequency is not very high. Why? Maybe the inductance impedance itself is small. The reactive part is small. So as you can see, we have here, it's not 25, sorry, it's 2.5. 2.5. So 30 component became 2.5. This is at order number 19, like that. So 19th order is appearing here, attenuated. But when we shift the harmonic orders to higher frequency, you will find that here you have empty space, no harmonic orders, and the first one is appearing around 1 point something, okay, at order number 49. Increasing the frequency more will shift the harmonics more. And as you can see here, the THD value for current, firstly it was 3.85, then it's decreased to 1.7 and then to 0.79. So this is the way, شباب, of controlling the harmonics in pulse width simulation. Just by shifting the voltage harmonic contents, shifting it to high frequency, this is already going to reduce the harmonics in current, like what you can see. Is it clear, شباب? Is the concept clear now for the sinusoidal pulse width simulation? Any question? Right, good. Now, as a conclusion, شباب, increasing the switching frequency shift the harmonic contents to a switching frequency of F switching. So if you have, for instance, frequency of 2 kilohertz, the first high order of harmonics will appear around 2 kilohertz, like what we could see in our example. Also, the higher the modulation index in under modulation, the lower the harmonic contents. There is a relation, شباب, or curve between the modulation index and THD value. You will find that if this is THD and this is modulation index, you will find that modulation index here equals 0, and here, for instance, equal unity. You will find that the THD value is like that. Sorry. So THD value will decrease with increasing modulation index. This is also shabab by making many experiments and observe the output. You can find that by increasing modulation index, the THD value will decrease. Also, the current THD value is load dependent. Load dependent, which means it depends now on the impedance. If the impedance is inductive, the current harmonics will be attenuated because it depends on the load impedance. Right. Now, shabab, we discussed the sinusoidal pulse width modulation. If you apply the sinusoidal pulse width modulation, you will find that the output values will be like that, shabab. Here is an example using sinusoidal pulse width modulation inverter with a DC length of 400 square root of 2. Why exactly 400 square root of 2, shabab? Because in DC, how we can get DC for the inverter? Simply we use rectifiers. And for rectifiers, if we have a 3-phase rectifier, the maximum possible volt we can obtain is the peak value of line to line. So if you have line to line of 400, the peak value will be 400 multiplied by square root of 2, which is, if you calculate this value, 400 multiplied by square root of 2, which is 565. So this value now, shabab, is 565. So this will be now the DC length of our inverter. The maximum possible output power, shabab, for fundamental can be obtained from this voltage will be 347. This is the maximum line-to-line voltage AC that we can obtain from inverter if we apply the sinusoidal pulse width modulation. Now, shabab, if we have a motor of 400 volt, what we can do? We need higher voltage now. So in this case, sinusoidal pulse width modulation is not sufficient because you can only obtain an output voltage, shabab, of this value, 0.612 of EDC. And when you multiply 0.612 by 565, you get the volt of 347. So we have a problem now. We cannot get the required voltage if we apply the sinusoidal pulse width modulation. Why? As you can see, we applied 400 line to line to the rectifier. We have a shabab rectifier. Okay, this rectifier is supplied by 3-phase, 400 volt, 400 line to line. Okay, this is now rectifier, and you have here the DC length, which will be now the 400 multiplied by square root of 2, and then we have our inverter. So if we apply sinusoidal pulse width modulation here, you will get 3-phase output as 347, not more. So what we can do if we need here 400 for the normal line-to-line loads, we need higher voltage shabab here. So we have some other techniques that can be used in order to increase the output voltage, even with the same value of the input voltage here. These techniques are different to sinusoidal pulse width modulation, shabab. These are selective harmonic elimination, harmonic injection, and space vector pulse width modulation. So we have 3 techniques that can be used for increasing this value. Right. Firstly, shabab, we need to understand the harmonics in 3-phase system. Now, shabab, what is the value of IN in terms of electrical circuit here?
Zero.
It's 0 if IA plus IB plus IC equals 0. And this is only in balanced 3-phase systems. صح?
Yes.
But as a Kirchhoff current law, if you apply Kirchhoff current law at that node, we can say now IN equals
the sum.
IA plus IB plus IC. طيب. For harmonics يا شباب, if you have harmonics in three-phase system, we have three different components or classification of harmonics. We have something called the positive sequence, we have something called negative sequence, and we have zero sequence. Positive sequence يا شباب, which means the harmonic orders will be flow in minus omega. And negative sequence is the harmonic contents which will be in positive omega. The zero sequence means the harmonic orders that have zero phase shift between the three phases. I know it may be you listen to this to the first time, but for instance شباب, now if this is phase A, what is the third harmonic waveform for phase A? You will find the third harmonic is like that يا شباب. Let me draw only the positive half cycle here. Okay, so you have here for phase A, this is phase A, this is fundamental, and this is here phase A. This line here is phase A, third harmonic. ماشي? This component is the third harmonic of phase A. Type. As you can see, it's triple frequency compared to fundamental. For phase B يا شباب, you know that phase B will start from here, which is 120 degrees shift. So this will be phase B. What about the third harmonic of phase B يا شباب? It will have three components also like that. So you can find that phase B third harmonic is in phase with phase A third harmonic. Is it right? صح ولا غلط يا شباب؟
Yes, I.
So for all of time يا شباب, third harmonic current طبعا third or multiples, third, 9th, 15th, and so on. For third harmonic components, you will find that there is a relation for third says I third equals IA plus IB plus IC over 3. Because you add the three components, okay, together, and they are equal if we have balanced three-phase systems. So you will find all of time يا شباب, I third harmonic equals summation of the three-phase currents of third harmonics, okay, over 3. So here يا شباب, if we have third harmonic components here, you will find IN equals 3 multiplied by third harmonic components. Is it right? So if you have three-phase systems include harmonic, the third harmonic component will flow in the neutral wire, because IN is nothing but 3I third harmonic. Is it clear? Is it clear يا شباب؟
Yes.
طيب جميل. What will happen if we disconnected this line? Instead of having 4-wire three-phase system, we can have only 3-wire system. So what is the third harmonic current now يا شباب?
Zero.
It's 0. So it's prevented to move in the windings because it's open circuit now. The path of third harmonic component now is 0. For that يا شباب, we have 0 third harmonic current flow in 3-wire system, and also يا شباب in delta connected systems. So we prefer to connect motors as either 3-wire or delta connection. Why? Because there will not be any third harmonic currents. Even if you have third harmonic component in the waveforms, due to volt, it will not appear in current. Why? Because it's open circuit. And open circuit, شباب, it's like turning off something. If you have no path for current, so the current will be zero. So it will not flow. So this is very important note, شباب. In order to have third harmonic or remove the third harmonic from loads, just connect these loads as either 3-wire star connection or delta connection. In delta connection, it will be circulating in the delta and will not appear on lines, okay, on line currents. So we can make just something called third harmonic injection, شباب. If we added third harmonic component to the modulation waveform, the modulation waveform will increase and the harmonic content will not appear in the output waveform due to the connection. So third harmonic injection pulse width modulation is a technique used also to increase the output volt because the modulation index here became higher than 1, but at the same time it cannot be applied for 4-wire system. It can be only applied to 3-wire star or delta connection. Okay, شباب. Another technique is called selective harmonic elimination. It's more advanced techniques based on some Fourier analysis. We make some equations, شباب, for the output waveform, and we could find that we can solve some components or some equations in order to get zero harmonic order for any defined value. So we have like each harmonic order will have a series of equations like that. B1 equals function of alpha 1, alpha 2, alpha 3, and alpha 4, which are the notch angles of the technique here, alpha 1, 2, 3, and so on. So by this technique here, شباب, we will have fundamental component if we make it equal 1, fifth order make it equal 0, seventh equal 0, 11th equal 0. So now you force the converter to have 0 value for fifth harmonic, 0 value for 7th harmonic, 0 value for 11th harmonic, such that you have to fulfill the values of alpha. So in this technique, شباب, called selective harmonic elimination, based on these equations, which are almost fixed equations for all 3 phase systems, you just need to calculate alpha 1, 2, 3, 4. So we have here 4 equations. By solving these equations and getting alpha, we can apply this to our inverter in order to have unity fundamental and 0 value for some selected harmonic orders. For that, we call it selective harmonic elimination, شباب. This is also one technique. The last 2 techniques now we discussed, شباب, the selective harmonic elimination and third harmonic injection, can produce higher volt compared to sinusoidal one. So we use them along with the space vector, but no time to discuss space vector because it's very complex technique. So the important today, شباب, we try to focus is the operation of the PWM inverter and how we can remove the harmonics from current, and we said the effect of increasing the switching frequency of inverter. Everything is clear, شباب? Any question? Any question, شباب?
Clear,